All right, so we are going to begin with our notes for Unit 0, our summer work. We're first going to talk about linear expressions and equations. Some of this is going to be review from you. Some of it's going to be looking at problems in a more interesting way. So monomial versus polynomial. This prefix mono in monomial literally means one versus poly means many or multiple. So this first term here, negative 6a squared b to the fifth, it is one term. We have multiple things being multiplied together, but there's not multiple terms being added and subtracted. So we would call this m a monomial versus our red expression right there has some addition and subtraction going on of multiple terms. I can't combine them into a single term. So that would be considered a polynomial. Likewise, with our green and yellow examples, we have multiple things that are being added or subtracted. So you would think they're both polynomials. However, I want you to notice that that green expression that we have could be combined into a single term here. We could rewrite that as 1x to the seventh. Thus, even though it looked like a polynomial before, technically we could classify it as a monomial, a single term. Now, the coefficients are numbers that are being multiplied by our variable terms. So in this first monomial, that negative 6 is our coefficient being multiplied. In our second polynomial, we have 7, 8, and technically, we would not want to have negative 3 in there. It does have an x to the 0 being multiplied by it, but coefficients are technically numbers or constants that are being multiplied by a variable that does not have a degree of 0. Likewise, for our green expression there, 1 would be that coefficient. And then for our last expression here in yellow, we would have 7 and a negative 1, right? Because there is technically a negative 1 being multiplied by that p squared. Then we have constants, which are just numbers that are being added or subtracted to our variable terms. In this first expression, we don't have any constants, so I'm going to put NA there to say that there are none. Versus in the red one, that negative 3 is a number being added or subtracted to our expression. There is no constant being added or subtracted in our green expression. And then in the yellow one, we have a positive 9 that is being added to those variable terms. So that ends up being our constant. Now we want to talk about the degree of each variable versus of each term. The degree of a variable is just the highest exponent of that variable. So for instance, the a to the second power, that degree of that term would be 2. And then for the b to the fifth, that degree would be 5. But the overall degree of that term, negative 6a squared b to the fifth of a single term, that's all being multiplied together, I would add those exponents together and get a total degree of 7. Next, for our red expression, the degree of each variable, x is to the first power, that y is to the first power in the second term. And the degree of each term, because they're not being multiplied, I don't add those exponents together, right? Think about your rules of exponents. So the degree of each term for each of those is also just 1. I want you to notice we could say the degree for that very last term, negative 3, it's being multiplied by a variable raised to the 0 power. So I technically could list a 0 there for that 3 again. In my next one, the degree of my x to the 7th power is 7. There's no other variable being multiplied in that term, so the overall degree of the term is also 7. And last but not least, for 9 plus 7p minus p squared, the degree of each variable term is going to be 1 for that 7p, that p is raised to the first power, and then minus p squared, that p squared is being raised to the second power. Then the degree of each term, again, that 9 technically has an x to the 0 as that exponent, so the degree of that first term is 0. And then because those last two terms are not being multiplied together, the degree of the variable is the degree of each of those terms on their own. Last but not least, the degree of the polynomial is the highest degree in any of the terms of the polynomial. For our first one, there's only one term. Its degree was 7, thus the degree of the polynomial overall is 7. For the red expression, each of those terms that had variables, each were 1. They're kind of battling it out for being that leading term, you would say. But the overall degree of the polynomial would still be 1. I don't multiply them together because they're not being multiplied in my expression. In 1x to the 7th, that 7 is the degree of the term. It's my only term with degree, thus it's the degree of the polynomial. And then last but not least, in that yellow expression, we had terms of degree 0, 1, and 2. The degree of the polynomial is the overall highest degree. Thus, we would say this polynomial is of degree 2. So example 1, we're going to simplify by arranging an order of decreasing degree. So I'm going to go from high to low degree. And then we're going to state the degree of the polynomial. So the first thing I'm going to do is check to see, can I have any terms that I want to combine? And I notice that I have a y to the fourth and a minus y to the fourth. Those cancel each other out. One's positive, one's negative with the same coefficients of 1. They're gone. Next, I notice I have a negative 7 x squared y cubed that can only be combined with another term that has variables x squared y cubed. So I look at that last term at the very back, has an x squared y cubed. It has a positive 1 coefficient. So I'm going to do negative 7 plus 1 and get a negative 6 x squared y cubed. Oops. Next, I want to see if I have any other terms with variables because I see there's a plus 5 if I'm trying to go in order of increasing or high to low degree. I want to see if I have any other variables. I do, that 2x cubed y. There are no other terms for me to combine it with, so I'm going to carry it down, plus 2x cubed y. And then last but not least, I notice that I have a plus 5 and a plus 8. Those are like terms. They're constants. They both have variables of degree 0, so I can combine those to make a positive 13. Notice my degree of each term goes from degree 5 to degree 4 to degree 0. I want you to notice that for this first term, I added 2 and 3, those variable exponents, to get degree 5. For the second term, I added a 3 and a 1 because that y has a hidden exponent of 1. And then the 13 is of degree 0 because it technically has an x to the 0 or y to the 0 or any variable to the 0 power attached to it. Okay, so I do have it in order of high to low degree, and then we want to state the degree of the polynomial. And that degree of the polynomial is the highest degree of any term in our polynomial, so that would be degree 5. Now we're going to subtract this expression from this other one. Now notice we are starting with a negative 9 plus a plus 2a squared, and I'm taking away the other polynomial from it. So I'm going to set up negative 9 plus a plus 2a squared, and I'm going to subtract the entire polynomial, 4a squared minus 3a plus 9 from it. Now notice I'm subtracting that entire second polynomial, so I need to distribute that negative into the parentheses. So I'm doing negative 9 plus a plus 2a squared, and then I have a minus 4a squared, a positive 3a, and a minus 9. I'm subtracting that entire polynomial. Now I'm going to go ahead and combine like terms. I like to go in order of high degree to low degree. I notice I have some a squareds there that I can combine. 2 and negative 4 make a negative 2. That variable stays the same, a squared. Next up, I notice I have variables of degree 1, that positive 1a and that positive 3a to make a positive 4a. And last but not least, I have my constants, a negative 9 and a negative 9. Notice they are the same sign. They did not undo each other or cancel each other out. Instead, I combine them to make a negative 18. All right, next we want to simplify this expression. I notice I have some terms that are being multiplied by binomials or things they're being multiplied. So I'm going to distribute into each of those parentheses. That way I no longer need to worry about those parentheses. For the first term, I'm going to distribute 4 into that parentheses to get 4x minus 8xy. Next, I'm going to distribute a positive y into that parentheses to get a positive xy minus 4y. I prefer always to write them in alphabetical order, so that's why I went xy instead of yx. You could write yx, it would give you the same one. And then instead of writing y times 4, typically we write the coefficient first. And in this last parentheses, I'm going to distribute a negative x. Notice I've been keeping the sign as distributing into it, so I don't need to worry about the subtraction later on in another step. So I do negative x times 1 to get a negative 1x or negative x. Negative x times negative 9y gives me a positive 9xy. Again, I wrote my coefficient first and then my variables in alphabetical order. Now I'm going to go ahead and combine like terms. I'm going to start with my terms of highest degree. Notice my highest degree is going to come from those xy terms, because those are of degree 2. I have x to the first and y to the first. So I combine those to get a 1xy, or you could just write xy. That's totally great. Ooh, I also have another one I should have combined in with it. Let's go ahead and add that in, that positive 1xy. Now, when I combine those all, I'm going to get a positive 2xy. Next, it doesn't matter if you choose to go with x or y first. Again, I always just choose alphabetical order. So I'm going to combine that 4x with that negative x, and I get a positive 3x. And last but not least, I have that minus 4y. There's nothing to combine it with, so I go ahead and bring it down. Notice I can't combine any of these variable terms because they don't all have the exact same variable. All right, getting into the more interesting problems. These are potentially ones that you have yet to see so far. We're going to solve for g of x in this expression. Notice here is g of x. There are a couple ways that you could go about doing this. You could try to see what terms you're missing on the left side that you want to get to have it equal to the right side, or you can isolate g of x. That's the approach I'm going to take. So isolating g of x, I'm first going to get rid of everything being added or subtracted to the side with g of x. So I'm going to subtract the 4x squared from each side. I'm next going to add a 3x to each side. Notice I'm putting those under the terms I'm going to combine them with to save myself a little bit of a headache. And I'm going to subtract 9y from each side. And now when I do that, I still have a negative 2 g of x is equal to, and now I can simplify what's going on that right-hand side. 7x squared minus 4x squared gives me 3x squared. Negative 10y minus 9y gives me a negative 19y. Positive 11x plus 3x gives me 14x. Well, all that's left to do is to get rid of this pesky negative 2 that's being multiplied by g of x. Well, I'm going to divide everything by that negative 2. Remember, when we use the division property of equality, everything in my equation gets divided by the same number. Beautiful. Now g of x is isolated. It's on its own. You can leave all of these as fractions if you can't simplify them to a whole number. Like this first term, I'm going to leave as negative 3 halves x squared. The second term, I'll simplify to a positive, 19 halves y. And the last term, I can simplify to a whole number, so I should, to a negative 7x. In this class, it is highly encouraged that you leave answers as improper fractions. Mixed numbers, they're great if you want to use them, that's fine. But decimals, a lot of times you're going to encounter decimals not like these, where they're not nice numbers. Leave them as an improper fraction. Okay, now we want to find values of a, b, c, and d so that this equation is balanced. It's true. The first thing I'm going to do is get rid of these parentheses and try to combine some terms or notice which terms go together. So I'm first going to distribute this negative into the second parentheses because I'm subtracting the entire thing. I have a negative 1 being multiplied by it. So I have 3x cubed minus 2ax squared plus bx plus 1. And then I have a minus cx cubed, a minus 5x squared, a plus 7x, and a minus 9. Notice each of those changed sign that was inside that parentheses. Okay, now in order for this equation to be true, I know that all the x cubes on the left-hand side of the equation have to equal all the x cubes on the right-hand side of the equation. So I have 3x cubed and a minus cx cubed on the left, and that equals a negative 1x cubed on the right. So I can set that up. 3x cubed minus cx cubed have to end up equaling a negative x cubed. Well, if all of those involve x cubes, I set them up to say, hey, those all go together because they have the same variable type. Now I can disregard the variable completely and say, hey, those coefficients, they all have to line up. Well, now that's an easy equation for me to solve for c in. I'm going to add c to each side. So I get 3 is negative 1 plus c. I'll add 1 to each side to get that 4 is that value of c. Now I'm going to continue doing that for all the different variables that we see here. Next, I'm going to do my x squared terms because I know on the left, the x squareds combine to make that x squared that's on the right. So I have negative 2a x squared minus 5x squared is equal to 1x squared. Well, they're all in terms of x squared. Now I can get rid of the variables and say the coefficients have to match up. So negative 2a minus 5 is equal to 1 because there's a 1 in front of that x squared. Add 5 to each side to get negative 2a is equal to 6. Divide by negative 2, so a is equal to negative 3. I'm going to go ahead and continue. Next, I'm going to do my x terms. I notice I have a bx, a 7x, and that equals a negative 2x. So I'm going to say that bx and 7x are the only terms that can combine to make that negative 2x. Well, they're all in terms of x. Now I can say that their coefficients have to line up. So b plus 7 has to equal negative 2. Let me subtract 7 from each side to get that b is negative 9. Last but not least, I'm going to go ahead and do my constants. I have a positive 1 and a negative 9. Ooh, and those equal a positive 4d now. So I'm going to say 1, oops, let me turn this back on. 1 minus 9 has to equal a positive 4d. Notice none of those have x to a power or anything like that. They are all the constants together. Well, that's negative 8 is equal to 4d. Let me divide each side by 4 to get that negative 2 is that value of d. Now notice if you plugged in all those values back into our equation that we just found, you would indeed have that the left-hand side of the equation simplifies exactly to the right-hand side of our equation. Okay, we only got 3 more left here in this one. So we're gonna solve this equation now. So we're moving on a little bit from expressions in order to solve for a variable here. A little bit more typical than our last example. Let's go ahead and start by distributing into our parentheses so that we can combine some like terms. So I have 8t minus 20 plus 7 is equal to 3t minus 58. I'm going to combine like terms on the left-hand side together to get that 8t minus 13 is equal to 3t minus 58. I'm going to move all my variables to the left-hand side to get a 5t. I'll move all my constants to the right-hand side, so I'll add 13 to each side to get a negative 45. Now I divide each side by 5, so I get that t is negative 9. And I want you to notice that if I went back and plugged that into my original expression, and I simplify each side, I do indeed get a correct equation that negative 85 does equal negative 85. So my answer is correct. For a lot of our problems, you won't need to go through and do this check solution, but it's worthwhile for these next couple examples to see why. Let's go ahead and solve this next equation. I'm going to distribute again into my parentheses. Notice in the second side of my equation, the right, I'm going to distribute a negative 1 into my parentheses. I'm going to combine like terms on the right-hand side. So I'll combine that 3a and the minus a to get 2a. And I want you to notice I got 2a minus a equals itself, 2a minus a. Well, no matter what a is, that's always true. Something equals itself. So no matter what a is, this equation is true. This is a case where an equation solution is all real numbers. And that would technically be what you write as your answer. That a is all real numbers. Because you had something equal itself, that's always true, no matter what that variable is. And last but not least, we can compare that to example 8 right here. Again, I'll distribute into my parentheses. So I have 3/5 times m plus, now I'm going to multiply 3/5 times 10. Notice that 10 is over 1. I want to simplify this as much as I can. I would highly encourage you to try simplifying this before you multiply. Like notice that you could divide a factor of 5 on top and bottom, and you would get a value of 6 here. Or if you distribute it and multiply it across the fractions, 3 times 10 gives us 30 on the top, 5 times 1 on the bottom gives us 5. Notice that does indeed equal to 6 here. And that equals 2k minus 7. Ooh, sorry, that should be an m. It'll be fixed for you guys' notes. Okay, now we're dealing with we're dealing with fractions here. I'm gonna decide to move my variables to the right-hand side and my numbers to the left-hand side. I'm gonna add 7 to each side to get a 13 on the left. I'm gonna subtract 3/5 m from each side, and I can't do that in my head, so I'm gonna subtract 3/5 m here. And then I'm gonna rewrite that 2 with a common denominator as my other fraction. Now on the right-hand side, I can do 10/5 minus 3/5 to get 7/5 times my variable m. And then I'm going to get rid of that fraction being multiplied by using the property of its reciprocal. If I multiply each side by its reciprocal, the 7 multiplied and divided cancels out, same with the 5. So my variable m is in fact all alone. I can't simplify this because 13 and 7 don't have any common factors here. So I'm going to multiply that 13 across the top, the 1 across the bottom to the 7. When I do that, I end up getting 65 on the numerator and 7 on the denominator. Again, do not change that to a decimal. That's a horrible, ugly decimal. We don't need to consider it. Just leave it as an improper fraction because that's the exact answer. Okay, thanks for coming to your first summer lecture. Bye.